sunshine. Or, oh no. Oh no. Did you just call it Udo?
And, oh, my BC kids call this because, yes, I don't. Okay, so let me ask you this. When we first started talking about antiderivatives, I think I gave you something like this. And what did you tell me? Okay, so what's the answer, Marcus?
What?
So what's the answer?
I don't know. Well, 5 times negative cosine x.
Is it 5? Okay. Since if we were to take the derivative, Marcus, we'd have to multiply by 5, right? And the 155 would cancel out. Okay. Technically, this is u substitution. You just didn't know that you did it. Okay? Now, Marcus, what did you call it before I picked on you to give me the answer?
Chain rule.
Okay, you said the reverse chain rule, right? And essentially, that is what's going on. Now, we can do this one without technically having to do u substitution because it's just a simple coefficient of a linear term inside, okay? When we can't do it just in our head is when we have something a little bit more complicated, like maybe we have an x squared in there, or x squared plus 17x, or things like that, okay? So what we are going to focus on is essentially the reverse chain rule, all right? So let's think about this. We know that the derivative of a composition function, we have to take the derivative of the outside and then multiply by the inside. Do you agree? What do we call that? Chain rule. Okay. So if we have something that looks like the chain rule inside of our antiderivative, then that is what our antiderivative would be. So essentially what is going to happen is we're going to have to recognize the composition that will give us this chain rule, okay? So what I want you to notice is that when we use u substitution, we're going to be doing this right here to get to that. We're going to have a composition in order to be able to use the chain rule. What do I mean by composition?
Function inside a function.
A function inside of a function. If we have a function inside of a function, then that should be kind of a warning sign. Maybe I can try u substitution if I can't simplify this to work. Okay? Now we know that we have techniques like rewriting that we can use, right? Where we can either like multiply out or divide to simplify, things like that. But if one of those rewriting techniques will not give us something nice to work with, and we have a composition, we can try u substitution, okay? What I want you to write down, don't worry about writing that down, that's kind of what I talked about. Paraphrase this, maybe just write in your notes that we need to look for a composition, okay, when we're using u substitution. And typically what we're wanting to do, like, have you seen me giving you any antiderivatives with u's in them?
No.
No, okay? So we're like creating a u, like we're gonna call u something. And whatever is inside your composition, that's what you're gonna want to let u equal. Okay, we're gonna make a substitution where we're gonna let u equal whatever's inside of our function. Okay, now I'm going to give you a list of steps on the next page. And right now, it may not make a lot of sense because we haven't gone through the process. But what I'd like you to do is write them down so that as we go through the process, we can kind of go back to the steps that I gave you. Okay? So, how do we substitute? First of all, and this seems pretty understandable, we have to define what u is. Okay? Like I said on the slide before, you're going to want to try to choose the inside function of a composition to let u equal that. Okay, so do you agree that we have a differential inside of any antiderivative? Okay, like when we set up an antiderivative, I give you blah, 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 dx. Right, we have a differential, okay? Which means whatever we let u equal, we also have to think about what its differential is, okay? So you're going to differentiate and write it as a differential for u. All right? So what will end up happening is you'll have du equals blah, 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 dx. Okay. The whole point of choosing a u will be to rewrite our integral. So you're going to rewrite your integral in terms of u's. Whatever your original variable was, more than likely x, you're going to rewrite everything based on the u that you defined in that first step and the du that you found in the second step. Once you have rewritten your integral, then you're actually going to evaluate it. And then, was u the variable we had from the very beginning? No, that's not what the problem was originally written in. And so you're going to want to go back and you're going to replace your u's with whatever you defined it to be. So basically, you're going to take your answer and you're going to write it back in terms of the original variable. More than likely, yes. Okay. Now, we have a lot of techniques to take derivatives. We do not have that many techniques to take antiderivatives. Like, there's significantly less of them. So there are a lot of different cases that we can see with u substitution, which is why we're spending the next 3 days doing it. Okay, so we are going to start out with very basic stuff today, and we're just going to continue to build for the next couple days. So, first one, write it down. Okay, so like I said earlier, we're typically looking for a composition, right? And a composition with something left over too. You don't always have to have something left over, but you're going to see it more times than not. Okay? So when we're looking at the composition, which piece of this is the composition? Okay, the x squared plus 1 is being raised to the 50th power, right? You want to multiply that out? Nope. Now, if that was like x squared plus 1 squared, some of us may want to just multiply that out and then multiply it to the 2x and use the power rule. But the 50th power, no. Just no. Not a chance. So, we're going to take the inside of our composition and we're going to let u equal what is inside. After we define u, we're going to take the differential, okay? So, yeah, you can write du dx equals 2x, but do you remember when we did differentials where we wrote du equals 2x dx? Basically, like we split up the dy and the dx. Let me do this. Don't write this down with me. We're taking the derivative of u with respect to x, and it is 2x, right? When we talk about differentials, we can basically separate the du and the dx to two separate sides. Okay? We've done this once. We can think about it in our head. We're always just going to go straight to this. Now, if you want to write this step, that's fine, but I'm always going to go straight to here. Okay? Now, 2x dx. Do you see that anywhere? So 2x dx is du, right? So this is what we're going to do. This becomes the integral. X squared plus 1 is now u, and it's raised to the 50th power. 2x dx, well, that just is du. So we have the integral of u to the 50th du. That worked out pretty nice, didn't it? Okay, power rule. When we take the antiderivative, this becomes u to the 51st times 1 over 51. Is that your final answer? No. We need to change it back. U is x squared plus 1. So we will substitute x squared plus 1 back in. What do you think?
Where did you guys?
Well, since du equals 2x dx, we replace all of it with du. Does that make sense? Okay. Should we look at another one? Of course we should. Okay, do we have composition? We sure do, and we have a little bit left over, so that's good. If we're going to use u substitution, okay, it's really our only option here. We know what the derivative of cosine is, but not the derivative of antiderivative, excuse me, of cosine x cubed, and it's being multiplied to something. Some of you are already seeing that there's a relationship here. What would we let u equal if we wanted to use u substitution? X cubed is inside of cosine, which is why we would want that to equal u. Okay, we want to be as basic as we can. So x cubed is inside, which is why we're choosing it to be u. Look at this. Du would be 3x squared dx once again, 3x squared dx. I see that right there. Which means this is going to become the antiderivative of the cosine of u, and then 3x squared dx becomes du. Okay. Antiderivative of cosine. Sine of u plus c, but then we'll go back and change it to the sine of x cubed plus c. Thoughts, observations? Okay. Try this one. When you get an answer, compare it with your neighbor. Make sure you and your neighbor have the same answer. If you don't, figure out why.
Yes.
Remember the answer? Good. Yeah. Part one, what are you getting for an answer? Awesome. How do you feel about that? Okay. In the three problems that we've done, have you noticed that what is inside the derivative is conveniently multiplied on the outside? Have you noticed that? Okay. Now, these are set up pretty nicely, okay, for a reason. These are the first ones we're doing, okay? They're not always going to be exactly what we need. All right, so let's look at a case where that's maybe not for you. Don't panic. Okay, so we notice that this is a composition. Okay, there's a cubic function inside of the radical. Okay, that's our composition. Now, we have a cubic function on the inside. What kind of function is being multiplied on the outside? Squared. Okay. So we have an x cubed inside and an x squared outside. Is that at least a nice relationship? It is, okay? When we take the derivatives of polynomials, they lessen by 1 degree. So if we're going to use u substitution, it's our only option, it's good that if x cubed is on the inside, then at least we have an x squared on the outside, okay? So inside of our radical, we have 5x cubed plus 4. That's what we need to let u equal. Okay. Now, du would then be 15x squared dx. Do you agree? Okay. Well, this is home. We do not have 15. Do we have x squared? Dx. We have x squared dx. But we don't have the 15. So this is what we can do. We can divide that over here. We can divide the 15 over to the other side. So 1 over 15 du is the same thing as x squared dx. Now I have a substitution that I can make. Okay. So we have the square root of u, which I'm going to write as u to the 1/2. And then x squared dx is 1/15 du. So I'm going to throw the 1/15 on the outside because it's a constant. We don't need it till the end anyway. And then the du at the end where we like to see the differential. Okay. How do you feel about that rewriting? Any issues with it? Okay. So now I'm going to do the power rule. This becomes u to the 3/2 times 2/3, which is also times 1/15 plus c. And then to get to the answer that I want, we will have to rewrite this as, first of all, 2/45, and then the u is really 5x cubed plus 4 to the 3/2 plus c. Okay. Another one. This is our last true do it all the way through example, and then I have a couple antiderivatives that I just want to talk about but not actually solve. Okay, so this looks very similar to the cosine one that we did earlier. What's our composition? Sine of x to the 6 is our function, or our composition, excuse me. And inside of sine is x to the 6. U is x to the 6. That is inside of a function. And you're going to do enough of these problems that you should have some vision, right? What do you notice? Okay, so you notice that there is an x to the fifth, and you know that the derivative of x to the sixth is 6x to the fifth, right? So you know we're going to be able to keep going with it, right? Because what the derivative of u is, we have left over in our integral, okay? So what Chris mentioned is, well, we have x to the fifth dx, but we don't have that 6. So what do we do with the 6? We divide it over. So 1/6 du is the same as x to the fifth dx. Remember, we're making substitutions. We have to be exact. Right? So when we rewrite this integral, we do have this sign of u. X to the sixth is u. And then x to the fifth dx becomes 1/6 du. So we get negative 1/6 cosine of u plus c. So you're at the negative? For sure? Okay, don't second guess yourself. Be confident. So negative 1/6 cosine of x to the sixth plus c. Okay, maybe you're a little unsure about your answer. What could you do to check? Besides look it up in the back of the book. Maybe you're on a worksheet and I don't have the answer to those yet. Take the derivative. If I take the derivative, we should get back to there. And yes, we would need to use the chain rule to take the derivative. Okay? You can check your answer by taking the derivative. Okay? Now, I want to give you a topic for discussion. I have two antiderivatives here, both involving composition. Talk with your pod. Can we use u substitution on either of these? Talk. All right, so what do we think about the first one? Can we use use of substitution up here with this composition? Will's shaking his head pretty emphatically. Why?
Because there's nothing to be multiplied on the other side.
Okay. So if we let u equal 2x cubed plus 3, that's a squared, du would equal 4x. We don't even have an x. Okay? U substitution is not going to work on that composition. What's your only option in that first example? Multiply it out. Not a big deal. It's just a squared binomial. That's an easy one. Okay? Multiply it out. Do the power rule 3 times. Okay, what about this second one? Can we use U substitution on this? You said earlier on this one there's nothing left over. Okay, well we have something left over here. Can we use U substitution? Joe?
No, because there would be an x left over.
Okay, here U would be x squared cubed plus 2. But du would be 3x squared dx. Okay? So some of you saw right away, hey, these aren't matching up, right? They're not that one difference like we like to see. Okay? Here again, you're going to have to multiply it all out and do the power rule. Okay? So some of us might have seen these quicker than others. That is fine. I just introduced you to the topic. All right, but as you do more and more of these antiderivatives, you're going to be able to have more and more vision of where these problems are going to go. Okay, some of you would have set this up and then gotten to the 3x squared and be like, oh shoot, that's not going to work, erase, start over. Some of you are going to look at it and be like, oh, that's not going to work, and go to a different. It's okay, but as long as we can understand when it's going to work and when it's not, that's what we need to be able to do. Okay? So we have 10 minutes left in class. I would like you to open your books and I would like you to get started on your assignment. If you could get 2 problems, even 3 problems done before you leave, I would go a lot more comfortable. Okay, you have 1, 2, 3, 4, 5, 6, 7, 8, 9 bolded problems. So if you could get a third of it done, that would feel nice, right?